Well, greetings, everyone. Good morning, afternoon, or evening to wherever you're logging in from here today. It's great to have you with us today. And we have a mix of press, friends, scientists, and partners on this call today. Welcome to our first Schweickart Prize briefing. I'm Danica Remy, president of B612 Foundation. And on behalf of the Schweickart Prize team, I want to thank you all for joining us today. In today's webcast, Apollo 9 astronaut and B612 and Asteroid Day co-founder Rusty Schweickart will have a conversation with the inaugural Schweickart Prize winner about their proposal and its technical overview. Following that, we'll allow time for questions submitted by the audience. Members of the press, please identify yourself with the name of the publication in your chat along with your questions. All questions will come to our team. And with that, I'll begin by providing a little bit of background on the Schweickart Prize. Next slide, please. Welcome, everyone. I'm Danica Remy, president of B612 Foundation and the home of the Schweickart Prize. In advance of Asteroid Day this weekend, we're very excited to share the inaugural Schweickart Prize winner. Rusty and the first Schweickart Prize recipient will discuss this year's winning program winner and their proposal. For those of you who are new to the Schweickart Prize, the prize was created in 2023 in honor of Apollo astronaut Rusty Schweickart for his contributions in space exploration, business, and planetary defense. Awarded annually surrounding International Asteroid Day, which is this Sunday, the prize targets graduate students and early career professionals for their innovative ideas and potential leadership in the advancement of planetary defense. Before I hand it off to Rusty, I'd like to ask Dr. Ed Liu, who leads our Asteroid Institute program and is also the co-founder of B612, to say a few words about the importance of the Schweickart Prize.
Hi, thanks, Danica. I think the Schweickart Prize is incredibly important, not only for honoring Rusty for his tremendous achievements throughout, his career, thus far, I should say, because he's not done yet, even though he claims he's retired. But, the important work that Rusty has helped start in planetary defense, protecting the Earth, doesn't just happen by itself. It happens because people do it. And that's why I think this prize is so important, because it supports early career folks like Joe, who you'll meet in this work. And really, in the end, it's all about supporting the people who do the work. So congratulations, Joe, and thank you, Rusty, for your contribution.
Thanks, Ed. Launching the Schweickart Prize could not have happened without the prize founding sponsors. Today, we're joined by Matt Kent, CEO of Meteor Crater. Matt, can you say a few words about why sponsoring the prize was important to Meteor Crater and the Beringer family, who owns the crater?
Thank you, Danica, and we're just absolutely thrilled to be a part of this. Every day I walk out of my office and I get to stand on the edge of the most significant and prominent impact site on Earth. And I'm in awe of what it represents. I'm also in awe of what it represents in terms of risk and what could potentially happen. And that really just magnifies the work that B612 does. So when Danica reached out to us and gave us the opportunity to be a founding sponsor, I convened with the Beringer family, and it was a resounding yes. And it's because, not only is the work critical, and this is a great honor to put our name up there with Rusty in B612, but it's just important. And as Meteor Crater, we felt it was essential to be part of it and in partnership with it. And like I said, we couldn't be more thrilled.
Thank you, Matt, and to the Beringer family as well. And thank you to our other founding sponsors who helped launch this prize last year, including Anusha Ansari, Future Ventures, Jeff Notkin, the Jurvetson Family Foundation, Randy Schweickart and Michelle Hang, Rusty B. Schweickart, the younger, and Joanne Keys. Our winner today and in future years will receive a $10,000 cash award and a prestigious museum quality meteorite trophy. Now, over to Rusty for a few words on the context of the prize and our prize winner. Next slide, please.
Thanks, Danica, Matt, Ed. I'd like to say just a few personal words about the context for the Schweickart Prize. To me, this iconic Earthrise snapshot that the landers took on Apollo 8 was much more than a powerful incentive for the environmental movement, which it certainly was. For me, its significance is that it was the first time humans had actually looked back at Mother Earth from outside the womb. Several years later, I began to refer to this experience as the beginning of cosmic birth for Earth life. Next slide, please. About 2 months later, while I was outside the lunar module on my Apollo 9 mission, I had the good fortune to have 5 minutes while Dave Scott attempted to fix a jammed camera to truly absorb where I was and to ask myself, what's really going on here? While it took me several years to fully realize that experience, I came to see it as something much larger than a local historic event. What I came to understand was that this process of gestation and cosmic birth is built into the very essence of the universe, all the way from the Big Bang on, and that we here in our local neighborhood among the stars are the local representatives of that universal process. More significantly, I realize that we humans are a powerful agent, perhaps the most powerful influence in our long-term evolutionary future. In a real sense, we collectively are responsible for whether or not we make it successfully through this birthing process. Around the year 2000, we realized that the mass extinction that eliminated the dinosaurs and much of Earth life 66 million years ago was caused by an asteroid impact. Simultaneously, we were discovering more and more near-Earth asteroids. And so it became very clear that it was time to work on preventing this existential threat. To do that, Ed Lu and I and a small group of others formed the B612 Foundation. After all those years, what we can clearly say today is that we can do this. We humans can collectively meet this existential challenge. At the meta level, we are now technically able to slightly modify the natural clockwork of the solar system to enhance the survival of Earth life. This is the context of the Schweickart Prize and the challenge to be met by Joe DeMartini and many other bright young people who will follow in his footsteps. And so with that, I'd like to congratulate and introduce you to Joe DeMartini, Ph.D. candidate at the ISAE's Supero in France and the winner of the 2024 Schweickart Prize in Planetary Defense. Over to you, Joe.
Thank you, Rusty. And I want to thank everybody else for being here as well. I just want to say what a huge honor it is to have been selected as the first recipient for the Schweickart Prize. But without further ado, let's get into some of the details of my proposal. Can we get the next slide, please? So what I proposed for the Schweickart Prize was the SUnward NEO Surveillance and Early Twilight Detection Collaboration, or the SUNSET collaboration, as I'll call it. And SUNSET really came about through a conversation with a colleague of mine about the airburst event in 2013 over the small town of Chelyabinsk, Russia. So you can see in the image on the left side of this slide here, the sky trail for the Chelyabinsk meteorite as it entered the atmosphere and then exploded over top of this small town, caused all kinds of problems. Excuse me. And really the big thing that we were concerned about when I was discussing this was that we didn't see this object until very shortly before it entered the Earth's atmosphere. So on the right side here, I've got an orbital diagram where you can see the yellow ellipse is the orbit of the Chelyabinsk asteroid parent body, overlaid over top of the some of the terrestrial planets. And the thing to note about this figure is that everything is orbiting in a counterclockwise sense. And so if we wanted to try to see the Chelyabinsk parent asteroid before it hit the Earth, right at that green dot in the upper right side of the figure there, then we would have needed to look pretty close to the direction of the sun. And that really poses a lot of issues. The sun is very bright and it blots out everything else in the sky, making it really difficult to see things in that direction, anywhere interior to the Earth's orbit. And so this is the challenge that I tried to address with my Schweickart Prize proposal. The goal of which is to increase discoveries and improve tracking of near-Earth objects approaching from the sunward direction, and the method of which is to use ground-based twilight observations. Now, I've suddenly thrown a lot of jargon at you all, so maybe we can take a couple of minutes to go through it and make sure that everybody really understands what sunset is about. So let's get the next slide, please. So let's start with understanding what I mean when I say near-Earth objects approaching from the sunward direction, or sunward NEOs, as I'll call them. So on the left side here, I've overlaid a bunch of plots of the orbital families of the near-Earth objects, and I've singled out some of the ones that we're interested in on the right side so that you can see them individually. So what I mean by a sunward NEO is any object that spends a portion of its orbit interior to that blue circle that is the Earth's orbit in any one of these images here. And specifically, we care about the ones that cross the Earth's orbit, because those are the ones that have the highest chance of a potential impact. So what we're looking at are the Apollo asteroids, which spend most of their time exterior to the Earth's orbit and a smaller fraction interior. And this is what we believe the Chelyabinsk parent body was. But more specifically, the Aten family of asteroids, which spend a large portion of their orbit interior to the Earth and only a small portion exterior. Meaning, in order to see these, the asteroids in the Aten family during any large fraction of their orbit, we would need to be looking in the direction of the sun. And there are also the Atira family asteroids, which spend their entire orbit interior to the Earth. And so this is the types of asteroids that we're trying to look at. The issue is that we have to, in order to see them during some fraction of their orbits, we have to look in the sunward direction. So let's get the next slide, and I can explain what these twilight observations are, which will help us do that. So here what you're seeing on this diagram are a bunch of orbits of near-Earth objects in these blue lines here. And then we've also got the Didymos orbit singled out because this image was originally from the NASA DART mission. But for our purposes here, we'll assume it's the same as any of these other near-Earth objects. And then I've put this big yellow triangle on here to try to show you schematically. And I want to be very clear, this triangle, the dimensions of it are not backed by any numbers. It's just representative. But to try to show schematically the region of the sky that we're not looking at on any given night because it's contaminated by solar brightness. So there's this huge swath of the area interior to Earth that we don't see on any given night because we're not looking over there because the sky is too bright. And so what these twilight observations allow us to do is that once the sun is just below the horizon at sunset, or just below the horizon before sunrise in the morning, the very bright object of the sun is suddenly out of our field of view. The sky is still a little bit bright, but we can point our telescopes in the direction of the sun and not have the images be totally overexposed by solar brightness. So let's get the next slide, and you can see when we include these twilight observations, we suddenly shrink that yellow triangle and illuminate this large pink area that I've shaded in for you guys here. And this is the region that those twilight observations allow us to suddenly see. And so this is an area of the solar system on any given night that we can only see if we're using these twilight observations. And the real kicker is that twilight time for most telescopes is a time when they are not doing other science observations. And so if there's no other science going on, and it's a time when we can uniquely see these sunward near-Earth objects, then it just kind of makes sense to be looking for them and using our resources during this time to see these objects that we wouldn't otherwise be seeing. So this is the core of the sunset proposal. And this is what I wanted you all to really understand. So now that we know what sunward NEOs are, we know what twilight observations are, maybe we can move on and talk about what kinds of organizations can participate in the sunset collaboration. Let's get the next slide, please. So the primary observatory that I proposed for discovery in the sunset collaboration is the upcoming Vera C. Rubin Observatory, imaged here in some of these amazing pictures from their website. The Vera Rubin Observatory is what we call a survey telescope. And so it has a very wide field of view, can look at a large portion of the sky at any given time. And the telescope has a very large aperture, a large light collecting area. which helps it better differentiate what is an interesting object versus what is background sky with potentially less observing time. And that's critical because this twilight time only really lasts for about an hour or maybe less after the sun sets, depending, or before the sun rises, depending on how close to the horizon your telescope can point. The other thing that makes Rubin uniquely good for searching for objects in the sunward direction is that they have already published soft plans for a low solar elongation twilight microsurvey. These microsurveys for the Rubin Observatory are community-suggested projects to add on to the larger survey, which don't largely impinge on the nominal observing time, and which will be included if they can garner significant community support. And so twilight observations, as I've mentioned before, have potentially zero impingement on other science observing time. But what I'm hoping that that Sunset being awarded the Schweickart Prize will do is indicate to the folks at the Rubin Observatory that there really is a lot of excitement about these twilight observations. It's a lot of scientific merit, and that this twilight microsurvey can be included in year one of Rubin's operations, which will start a little over a year from now. So we've singled out the Rubin Observatory for discovery of sunward NEOs. Let's go to the next slide, and we'll talk about what we can do, what the collaboration aspect of Sunset really involves. So Rubin will be observing around twilight. It'll be imaging large swaths of sky and trying to discover some of these sunward objects. But these objects are highly transient. They go away very quickly, and it can be difficult for Rubin alone, with its survey cadence and the small amount of time that twilight observations allow us, to meet the rigorous requirements necessary to confirm the discovery of a near-Earth object. And this is where follow-up characterization comes in. We want Sunset to really be an international collaboration. And so any other twilight observatory can participate in this follow-up target of opportunity search. I've got an image here of the dark energy camera, which is just one example of a twilight-capable observatory. But what I really want to point out here is that once Rubin, for example, has found an object in the sky they think might be a new discovery of a sunward NEO, all of these other telescopes will know exactly where to look, precisely where to point. And that makes it much easier for them to get an observation than if they're sort of blindly searching around. So this is brilliant, but it's still difficult to combine observations from disparate observatories at different times of day or different cadences. And that's where we come into some of these novel orbit characterization softwares. For the Rubin Observatory specifically, there's the HelioLink 3D software, and from the B612 Foundation themselves, their new Thor algorithm, which can take observations from different times, even historical observations, and combine these from different sources and at different periods of the day, and combine them into high confidence orbits for any of these objects that we're looking at. So we're looking for objects with the Vera Rubin Observatory. We're pulling up with twilight capable observatories, and we're combining all of these observations with these novel softwares to create high confidence orbital refinement and confirm these discoveries. Let's get the next slide then to see about what the next steps of Sunset might be in the near future. So we can also try to include the Atlas Observatory network imaged on the left here. This is a network of telescopes, all with the same specs, which are supposed to serve as an early warning system. Asteroids on their, or near-Earth objects on their final approach, which will have close approaches to Earth, can be observed by the Atlas Observatory network, and we can get warning time far enough in advance, hopefully, for us to do something about them. Now, I know that the Atlas Observatory telescopes are capable of doing twilight observations. So if we can get them involved in Sunset, then they could be a really great close approach discovery or warning tool for these sunward NEOs. There's also the NEO Surveyor mission, which will launch a few years after Rubin starts operation. It will sit in an orbit, a space orbit, so it's a satellite, between the Earth and the Sun at what we call the L1 Lagrange point, and it will be an absolute titan of NEO discovery. But NEO Surveyor is going to get so much data that it will be difficult to follow up on it without an organized follow-up network. And this is where we think that Sunset could potentially link in, follow up on at least these SUnward NEO discoveries and help support the NEO Surveyor mission. The NEO Surveyor mission in turn support Sunset. So these are some of the next steps that I was thinking about when I was writing up my proposal. We'll go to the final slide, and I'll just do a quick summary of everything so far before we take some questions. The next slide, please. So just to go over everything one more time, I proposed the SUnward NEO surveillance and early twilight detection or Sunset collaboration, the goal of which is to increase discoveries and improve tracking of near-Earth objects that approach the Earth from the sunward direction, and using the method of ground-based twilight observations, focusing primarily in the proposal on the Vera C. Rubin Observatory for discovery and utilizing observations from a network of other twilight-capable observatories for follow-up and orbit confirmation, and combining all of these observations with the novel orbit refinement softwares that are being developed to facilitate that discovery confirmation. That is Sunset, and thank you so much to everyone here and to the folks at the B612 and all of the sponsors and organizers for choosing Sunset, choosing me. It's such an honor.
Thank you, Joe and Rusty, for your work and dedication to advancing asteroid discovery and planetary defense. And thank you to the Schweickart Prize team who are on the call today, that include Randy Schweickart, the prize chair, Rachel Morozpu, our Schweickart Prize manager, Colleen Frieschetti, and Delphine Vera Millen from our core B612 team. Without this team and the support of donors from around the world, B612 and the Schweickart Prize would not be possible. Having operated for over 2 decades, B612 is the only NGO in the world dedicated to protecting the planet from asteroid impacts.